We were looking at, we're talking about exoplanets, and exoplanets are worlds that are, these are planets that are not in our own solar system. So these are planets that reside in solar systems of their own, orbiting other stars. And we started by looking at the Trappist system, and we'll get back to that in a moment. Right now we're looking at the night sky from the Huntsville area tonight, facing sort of north. And I want to point out that when we look in the night sky, we can see all sorts of different things, and many of these things, there, we'll change it to some circles there, many of these stars that we can see do have planets of their own. So we're going to take off from the Earth, which is neat, with a 5, 4, 3, 2, 1. And go into orbit and take a look at some of these things here. Okay, awesome. So, let me jump into this once again and say that all of these little stars that you can see in here that are circled, these are all worlds where we have confirmed exoplanets. So through various different means, we have discovered some 4,100 and let's see, I believe it's 4,158 exoplanets to date, and there are about as many candidates as well that are under consideration. Now you'll notice that there's a really bright patch in the sky right in there. That's called the Kepler Field. And this is where a particular space telescope peered for several years, basically literally just observing this one patch of sky, trying to better understand what is going on with these various stars and looking for different light curves. So tonight, what I want to talk about a little bit is what different means we use to find different planets outside of our solar system, and to go and discover a few of them or explore a few of them, and show you a little bit of what we know. So that poll that you couldn't hear me talking about was more interesting because all of those items in the poll are actually 4 different means, the 4 most common means that we use to discover these different worlds. So I want to talk a little bit about that first, and then we'll jump into the worlds themselves. So perhaps the easiest way to discover another planet is to simply, I say the easiest way, the most obvious way to discover another planet is to simply take a direct picture of it. So let me show you what that looks like. And what you can see in here is a star, and it's obscured by an observing disk in here. We have a star, and we have little points of light that we can see that are moving around them, and these very, very faint points of light are indeed planets. So we can see how far away they are from the star, we can see how fast they're moving, and we can even get a small sense of their mass. So neat things in here. And if we bring this video down, we can actually model this system right in here. This is a system with these 4 planets in here, and you can see where they're orbiting their host star. So this is a very straightforward way to take advantage of discovering these different worlds, but it's a very difficult means because you have to have a star that's very close with planets that are relatively bright. They can't be too close to their star or they're obscured from view. We have to sort of have this top-down view. There are lots and lots of limitations, and so as a result we have only discovered 49 planets through this method to date. So it's not a very effective one. So 49 planets out of the 4,158 we've discovered is not so good. So jumping to another option. A much better option, one that we've discovered 802 planets is through radial velocity. So we're basically trying to figure out what's going on with this wobble. So a planet is going to be gravitationally attracted to its host star, and because of this, because there's a gravitational interaction between them, it causes the host star to slightly orbit around the shared center of mass with the planet. So typically that center of mass is within the star itself, and it's a very, very minor wobble, but it's a wobble that is detectable with a Doppler shift as that star is moving with respect to our solar system and from our point of view. So with that said, we can, let me show you that video one more time. With that said, we can take a look at the light that's coming and sort of see how the spectra is shifted from our point of view. And if we see this little wobble as the planet is moving around its host star, then we can say with some good certainty, if this wobble is periodic, that there is indeed a planet there causing this wobble. So again, 802 planets, exoplanets have been discovered in this way. So neat stuff. Okay, switching. Microlensing. This one is very complicated, so we're going to play it a couple times to sort of give you the idea. Okay, so you're seeing a star, and another star, and a planet. Okay, so the blue star that's sort of static right there in the center, that's very, very far away. The yellower star is closer, and it's passing in front of that star. When those stars get close together, the light from the farther away star is getting bent around, gravitationally lensed by the star in front of it, and it sort of brightens the entire viewing experience from our point of view. If you have the existence of a planet right there, then we are sort of off to the side, but within view, it extends the amount of bending of that light. It basically broadens the sort of gravitational well that light is moving through, and so it bends the light to a greater extent, and you can see that little blip as a result. So this is not a great method for detection, simply because you only really get this one shot, and it's sort of a you don't get to reconfirm, so you don't get a sort of a second test, but it does give us the ability to see planets that are farther away from their stars, because the farther away the planet is from the star, the greater the effect of this microlensing. If this is complicated, which it is, and you're struggling to understand it, don't worry. I practiced trying to say this to you several times to give the best explanation, and it's not straightforward. So you can read up more on that if you like, and if you have questions, you can post them in the comments afterward, and we'll monitor those. I should point out, since I unfortunately put my face over the credits, this video and the next one are from the European Southern Observatory and look very cool. Okay, so this method in particular is responsible for only 89 planets that we've discovered. There we go, we've got our credit. Thank you, Aaron. So moving on, let's go to the most popular and perhaps the easiest to understand besides imaging, which is transits. We're searching for shadows. If, from our perspective, a star is in our field of view and we have a planet move right in front of it, over a period of time, we get a dimming of that light curve, right? So the light coming from our point of view dims a little bit. By a little bit, I mean a fraction of a percent to maybe single-digit percent. Up to maybe, I don't know, it could be 10% perhaps. In some cases it's more, but that's very, very rare. Usually we're looking at like 1 to 3% or so. And one dip, doesn't necessarily mean much, but if you continue to get dips that are periodic, then we can say, again, that there is a planet orbiting around this, or something orbiting around it. It must be a planet if there's no light coming off of it. And that's pretty straightforward, and that's pretty cool. So this is a very nice method. This is the one that the Kepler Space Telescope used to great success, and now the TESS, which is the Transiting Exoplanet Survey Satellite, is using to great success as well. And this is giving us awesome data and allowing us to find all sorts of things. And we'll talk about more of what you can know from this here in a moment when we jump back to the Trappist system. The question was, can you make some of those questions go away? I thought I did. My apologies. Hopefully they're gone now. If they're not, let me know. Let's see. Or you should be able to hopefully click next, possibly, maybe. Okay. So this one's pretty straightforward, similar in straightforwardness to direct imaging, perhaps. And this one is responsible for over 3,000 planets. 3,164 were discovered. There is one more option that has been successfully used to find all of one planet. That is astrometry. So basically, we can detect minuscule movements in the star's relative motion to us based on gravitational interactions with its host star. So this is similar to radial velocity, but we're actually looking at movements of the star, and that's different than looking at the spectroscopy of it. So it's similar, but this is very hard to do and accounts for one planet discovery. So there are your 5, your big 4, your smaller 1. There are other means that are possible, but they haven't been done yet. So there you have it. Let's jump to our solar system, and let's take a look at its setup really quick, because I think that's sort of important before we jump on and take a look at different things. So I want to show you orbits, and I want to talk about what's called the habitable zone. And this is an important thing because the habitable zone is this region within our solar system, or in any solar system, in which liquid water can exist on a planet. So you can see this sort of yellowish circle and this greenish circle, and everything in between is the habitable zone for our solar system. You'll notice that Venus is right here within it, just barely, and Mars is within it, just barely. And that may be confusing to you because you're probably aware that they're not very habitable, quite miserable, in fact. So Venus is about as opposite from the Earth as you can get, in that it is incredibly hot, and the atmospheric pressure is about 100 times that of Earth. It would be like 300 African elephants sitting on you and would crush you instantly. Further, you have sulfuric acid rain, you have temperatures over 800 degrees Fahrenheit. It's very bad, right? Mars, on the other hand, is extremely dry. It's very cold, very thin atmosphere, lots of radiation, sort of an unpleasant place in a different regard. Neither has a lot of water. So how does this work then? It's not a direct indicator that water can exist, simply that, or that water does exist, simply a water can exist if the planet meets proper criteria. So when we talk about the habitable zone, for different worlds, you have to understand that we don't really know if they do have water on them. We simply know that there is enough heat from that sun, from that star in particular, to allow for water in liquid form to exist on the surface of a planet, given the planet meeting some sort of important criteria, like an atmosphere, like proper atmospheric composition, that sort of thing, proper mass and size and these kinds of things. Okay, so let me jump over to the Trappist system. Actually, no. Let's jump over to the Earth really quickly. and which is a beautiful place to be sure. I'll bring the orbits down, but I do want to show you the Test Spacecraft, simply because it's very cool. It launched about 2 years ago, and just over 2 years ago, I guess, maybe in April of 2018. And these are its different orbits. It started with, in red, we have the phasing orbit to sort of get it to where it needed to go, yellow to transfer it into its sort of commissioning, and then science orbit, which you can see in purple. And then it orbits around the Earth in a fashion like this, which I think just looks very pretty anytime we show off orbits. And the real exciting piece is taking a look at its field of view. So I told you that the Kepler Space Telescope sort of sat and looked at that little like plus sign in the sky for years on end, very, very carefully pointing, looking at hundreds of thousands of stars in that region. TESS is looking at a much wider swath, and every few months is changing up which panel it looks at. Like I said, it's just over 2 years into its mission. Its primary mission concludes on July 4th of this year, and should wrap up, again, the primary mission, but should get extended, and will continue looking at exciting things. And it's has a couple thousand, maybe 3,000 exoplanet candidates, maybe 49 of which are uncovered, and this red portion is where it's looking at the sky right now. So if we bring that field of view down and throw up some constellations, you can see that it's actually looking sort of in the direction of, if you look pretty south early in the evening, this constellation, I guess I can bring names up for you, but we've got Crater the Cup and Corvus the Crow and Hydra the Water Snake in there. And it's looking mostly in the southern hemisphere, but some of that is still visible from the northern hemisphere, so those are things that you can see in there. All right, so pull that down for you, and we're going to journey in the direction of Aquarius, because we're going to head over to the Trappist planets. So hold on to your seats, and if you were here from the beginning when I didn't have audio, again, my apologies. We're going to zoom over to that system and give you a quick look. So what's interesting about the Trappist system is that there are 7 planets, similar to our 8 planets, but this was the first system discovered, not that had that many planets, but that had very many planets that were actually Earth-like. And in fact, all of the planets in the Trappist system are about the size of the Earth, so that's pretty funky. So let's zoom away from their star, which should be pointed out is very, very small compared to the Sun. And there we go, we'll bring that over. So to give you an idea of how small, we are looking at about 12% the radius of the Sun, so quite tiny. We're looking at maybe 3,800 degrees Fahrenheit compared to about 10,000 degrees Fahrenheit for the Sun. And its brightness is about 0.05% that of the Sun. So very, very, very dim. This is a red dwarf, and it's a little bit older, maybe 7.5 billion years old. Very old, very dim, and very, very small. So what does all of that mean? Well, in order to be within the habitable zone, which we can pull up in here, you can see the same yellow for the inside and sort of green for the outside. You'll see that at least 4 of these planets reside within the habitable zone, but these planets are incredibly, incredibly close to their host star. And when we say incredibly, incredibly close, if they were modeled within our own solar system, and I can give you a sense of what that would look like. If they were modeled within our solar system, they're also sort of kicked by comparison. They don't have the same plane. They would all be well within Mercury's orbit. In fact, the closest planet to this, which is Trappist 1b. Trappist 1b is something that orbits around its host star every 1.5 days. So it actually orbits around every 1.5 days, and for comparison, Venus is about 88 Earth days. So this thing is zipping around. So this is, all of these planets were discovered by the transit method, and this is where the transit method really shines because, shines, or doesn't, because it's easy to make jokes when you're alone in your room, but the transit method is very effective when you have very short period orbits, because you can get a lot of them and then say with certainty, there's a planet moving around here every 1.5 days. If you have to wait, 365 days, then if you want more than one orbit, you have to wait 2 years, 3 years, 4 years. If you have a far away thing that's, a 10 Earth year orbital period, then you have to wait, 20, 30, 40 years in order to figure out if it's there, and that's not very effective. So these short period ones are very good. Like I said, 1.5 days for the closest planet. The next closest planet is like 2.4 days. Then we get up to 4 days, 6 days, 9 days, 12.3 days, and just under 19 days for the farthest away planet. They're labeled B through H as you get farther and farther away. So that's pretty wild. So again, these are all Earth-like in size, maybe 70% the size of the Earth, all the way up to perhaps maybe 1.5 times the size of the Earth, and similar in mass and that kind of thing. But I want to take you to planet E, so this is Trappist 1e, because this is perhaps the most Earth-like. This one and 1f are perhaps the most Earth-like of all of them. This one is just a touch under the size of the Earth, just a touch under the mass. Might be an ocean world, but probably or could have some land on it. And it is probably tidally locked, which means that the same face always looks at its star, and the opposite face never gets to see any light, which is problematic. But you can see an artist's conception of what this might look like. So keeping in mind that even though we have directly imaged some different exoplanets, we haven't seen the surface of anything at all. So, actually that's a question. So can we tell with imagery if they have water? We really can't. We can only see, roughly where they are. But we can tell various different things about them, because when we can figure out how quickly they're orbiting, right? That gives us orbital period. We know how long it takes them to orbit, which then tells us through mathematics and physics how far away they're orbiting away from their star, if we know the mass of the star. And if we know how far away they are, and we know that there are more than one of them, and we can see sort of small gravitational perturbations, then we can actually get a sense of mass based on how they're sort of tugging on each other, and that's pretty neat. And then if we can figure out mass, and we can figure out volume from basically the light curve that's being blocked, basically the disk that's being blocked, how much light is being blocked from our eyes, we can figure out volume. And if we know mass and volume, we can figure out density. So we can start to say lots of different things about them. And as our technology gets better, we'll be able to do spectroscopy, basically looking at the light curve from these planets themselves, or the light curve of the star as filtered through maybe a planet's atmosphere, and get a sense of what composition might be like. And so that's an exciting sort of thing for the future. And more on that hopefully soon when we get better and better technology. So that's one of the things that the W1st satellite space telescope, which was just renamed the Nancy Grace Roman Space Telescope, is going to look at, along with the James Webb Space Telescope. These are small applications of these tremendous flagship telescopes that are being worked on as we speak. So that's super cool. So this all raises the question, could you have life on a world like this? And we'll jump over to planet F just for kicks. Could you have life on a world like this? And the answer is, very, very maybe, I don't know. The difficulty, of course, is we can't get much better measurements than what we've got. And that doesn't tell us anything about life whatsoever. But it is certainly possible. We just don't have a very good way of knowing. The thing that needs to be stressed for the Trappist planets in particular is that a red dwarf, similar to its host star, Trappist 1, is something that is potentially fairly volatile in terms of radiation and can have sort of very substantial storms that could, of radiation that could be either sparking life, but could also wipe it out as well. So that's sort of a sticky scenario where it could be useful. It could also be extremely bad, and certainly life as we know it wouldn't do well. But perhaps life that's adapted to intense radiation bouts could be beneficial. I don't know. So here you can see still a water world, but a little bit icier of one because it's a little bit farther away. And if we were to zoom in to, say, planet C, for example, we'd see something that's sort of Venus-like and very, very hot with lots and lots of atmosphere. So I've been talking hard, largely because I haven't seen any questions. So if you have any of those, please do chime in if you have any. And let's see. I had lots of other things that, there we go, you can see a very cloudy world in here as well. Like I said, sort of similar to Venus. One thing that's important to note is that this system is actually fairly comparable to the Jovian system of Jupiter and its moons. So this star is sort of comparable in size to Jupiter, and the moon orbits are sort of similar as well to the Trappist system. So that's sort of a neat thing for us to compare and contrast as well. So what I'd like to give you now, let us jump over to the closest exoplanet to us, which is going to be conveniently next to, it's a planet orbiting the closest star. So this is Proxima Centauri star, known as Proxima b. So we'll jump over there right now. Similar scenario where the star is very, very small, and that's about 14% the radius of the sun, about 12% the mass, and about maybe 0.2% the brightness. It's about 4 light years away, 4.2 light years away or so. And it has roughly an Earth-sized star, or Earth-sized planet in Proxima b. Probably in the habitable zone. We have no idea what it looks like. This is an artist's impression, just like the other ones. It's probably less hospitable than the Trappist planets, but we can only really speculate. And that's sort of a neat thing. So I guess part of the difficulty in talking about exoplanets, the exciting thing in talking about exoplanets, is that it is a very up-and-coming field. It's a very new field of study simply because of the way technology has evolved very quickly in the last 15, 20 years. It's a great field of study going forward, if you're just getting into this sort of thing because, it's so new. So there's going to be so many opportunities in this, so many discoveries coming very soon. So it's a fun thing to look into and get researching. There are various different citizen science projects for you to help try to find exoplanets using exoplanet data. I'll scrounge up a link for that. Planet Hunters on Zooniverse is one of them. So Aaron, if you can find that, that would be great. And if not, I'll post it afterward. And you can explore further on a variety of different sites. And that might be cool for me to show you right now. So maybe let's do that. Let's see. Play around with all of my different windows I have going on here. And hope I don't crash everything. Okay, so we'll fade that out here for a moment. And if you've followed these live streams before, we like to use Worldwide Telescope, which is a free and open source planetarium software, which is available both on the internet, worldwidetelescope.org, which we'll link to. Also, you can download it on a Windows PC, so that's pretty cool and pretty easy to click and drag around and zoom in and explore different things in the night sky. We used it pretty extensively last week to take a look at what's up in the night sky. So I want to show you how you can explore where we found exoplanets further. And if you go to the search and kind of click the pull-down menu, a precision click on this little down arrow. If we go to this VO cone search, this sounds and looks very intimidating, like lots of data. And it is lots of data, but it doesn't need to be intimidating for you. You simply want to change your search radius to 180. Oh, you have to uncheck from view. Change this to 180, which gives you a nice wide field of view. And then you're going to search this whole registry, and it's basically going to pull down all sorts of data options for you, way more than you could ever want, perhaps. While that is downloading, sometimes it takes a minute depending on if the servers are backed up. Colin asks, what percentage of stars which have exoplanets are dimmer than our sun? Seems like everything is fractionally bright, or maybe just the two we picked. That is a great question that I don't know off the top of my head. I did pick two that are dimmer, but I don't know. And actually, this is a way we might figure it out. So you can see endless catalogs of various things, and that's sort of overwhelming. But if we simply type into here exo, and then run the search once again within all of these things that have been found, then we can come across the NASA Exoplanet Archive, conveniently the first thing there. And we want to search within this 180-degree field of view. Once we've clicked that, we click search right there. It's going to populate with all these options for us, and every single one of these little points is what I showed you in that other software, Digistar 6, which is what we use in the planetarium. And you can see the Kepler Field in here that we saw before. You can see all these different planets, different candidates at these stars, which is a very powerful thing. And you'll notice that this is up to date completely, 4,152. That's pretty cool. It also tells you every single one in here. So one thing that we could do with all of this data, which might be wildly overwhelming, let's make this a good bit bigger. There we go. On the NASA Exoplanet website, you can, it's the Exoplanet Archive, which we'll also link to, but looks like this. You can explore here further and get an idea of what all these different abbreviations mean. PL means planet, ST means star, that kind of thing. So what we could actually do is sort of cruise over here until we get to the different star values. We could sort by stellar distance. We could sort by stellar temperature. We can sort by things like stellar mass, if I can find it in here. There you go, star mass, if we have it. Should be star radius. There you go in there. So what we might do, we have all of these things circled, and we have their coordinates in here in right ascension and declination. We can change their size based on, let's see, star radius. So we'll pick that in here. I haven't done this for the record. This is, I have no idea if this will actually work or not, but I hope it will. And in theory, things will change. They did not. Awesome. That was a bad tutorial, I guess. So there are ways that you can do that. I didn't attempt this to try to show you, but basically you can explore further. In the same way, you could sort these things around and play with different things and see, you know, what sort of stars we're dealing with. Big ones, small ones. Otherwise, you can see some are about the size of the sun with 1. Some are 22 times the size of the sun with 22. You have a 13. You've got a 0.9, a 0.7, a 40, a 50, 0.7. So they're sort of all over the place. 0.5. So there you have it. And I think STRAD means stellar radius. I could be wrong there as well. I again didn't prepare for that, but gives you an idea of what you can do and explore further, and see what else lies in these various regions. So that's sort of a neat thing. Okay, so let's see. Last question before we wrap up for tonight. Could we use the SpaceX model of cheaper satellites to create cheaper relays to extend what we can see? Is that something that would be workable or fail because getting the telescope far out to make a difference would cost too much fuel? Let me see if I fully understand the question. So I think my understanding of what you're asking is that if we were able to put up a constellation of satellites, very cheap ones, sort of lots of them at very cheap, could that sort of enhance our telescope to get lots of different data points and sort of see from different angles maybe and collect more data? Maybe. I guess it would depend on what type of observing techniques you're looking at. For transits, I don't think that would be effective. For like Doppler shifting or lensing, it might be effective. If you could, I mean, a lot of telescopes, if you're looking into just sort of small patches of sky, that would help us find different things. But I don't know that it would extend our depth of view. It might extend our sort of breadth of view, our width of view. So that might help if I'm understanding your question adequately. Cool. So, happy exploring. I hope you take advantage of some of those things. And actually one more slide to show you just for kicks because I think it's really pretty. The Trappist 1 website has some cool abstract art. Looks very pretty, and you can get all sorts of neat graphics and information about these various things. Again, all artist conception, but pretty cool, and all sorts of data, all sorts of neat comparisons within their own system, within our system, these sorts of things to other exoplanets. It's a very, very neat website. So Trappist.1, we'll link to that one also. So with that said, if you have any other questions, post them and we'll answer after. But thank you for bearing with me despite a huge mess of not having any audio for the first few bits. I told you some great things too in that first 7 minutes. But thank you for bearing with me. Remember that audio or otherwise, science never stops, not at the U.S. Space and Rocket Center, nor anywhere else. And you can come visit us now. We're reopening here at the U.S. Space and Rocket Center, the museum, that is, not yet the planetarium, but the museum will be reopening next week, and you can find out more information on our website at rocketcenter.com. And we hope to see you very soon, safely. So stay safe, come visit us, and thank you so much. My name is David Weigel. I hope you have a great evening, or whatever time it is for you. See you next week. We'll be talking all about our moon in exquisite detail. Thanks so much.